This question is about equilibria. Give two features of a reaction in dynamic equilibria. So we're looking for two ways that we can show that a reaction is continually moving, but the amounts of our reactants and products are staying the same. So we're looking for, imagine you're going up an escalator, the escalator is coming down and you're walking upwards. How could we be moving and yet staying in the same place? And that would happen if we were going at exactly the same rate as the escalator. So we say, in chemistry, we say that the forwards and the backwards reactions are going at the same rate. So not are the same, but their reactions are at the same rate. Or we could say their rates are equal. And as a result of that, the concentrations of the reactants and products will remain constant. They're not the same as each other, they're the same as themselves, they are constant. A gas phase reaction is at equilibrium when the pressure is increased. So when P goes up, yield goes down. What that means is that equilibrium shifts to the left when pressure increases. So if you think about a reaction, and if we're going to be, this reaction has equal moles on each side, and if we were to increase pressure, we would shift to the side with the fewest moles, but there is equal moles, so that wouldn't move. So when we increase pressure, we're going to shift to the side with the fewest moles. We said we're going to shift left, which means we need to have more moles on the right-hand side in order for us to be able to shift to the left when we increase the pressure. The equilibrium has a greater number of, and we only look at gas moles on the right hand side, or the product side, you could say. Carbon monoxide and hydrogen react to form methanol. A 0.430 mole of carbon monoxide is mixed with 0.86 mole of hydrogen. At equilibrium, when the total pressure is 250 kilopascals, the mixture contains 0.110 moles of methanol. Calculate the amount in moles of carbon monoxide present at equilibrium. Now, there's lots of different ways to approach this calculation. I'm going to use the method that looks at the initial amounts, the change, and the equilibrium amounts, sometimes referred to as ICE. I like to call it RICE because I'm going to put the ratio down as well. So I've got ratio 1 to 2 to 1. That's just the numbers in front of the chemicals in the balanced equation. The initial amounts, 0.430 moles of carbon monoxide, 0.860 moles of hydrogen, and at the start we have no methanol. And then it says at equilibrium, so on this E line, I've got 0.110 moles of methanol. So what we can see is that the change for methanol is that it's increased by 0.110. Now the reason I put the ratio in is because the ratio and the change need to be in the same proportions. So 1 to 2 to 1 is the same as watt to 0.110. So every time there's a 1, we can have 0.110. How would we go 1 to 2 to 1? We'd have to double 0.110 to 0.220. And then we remember that our reactants, if we just divide the reactants from the products, our reactants decrease while our products increase. And the question is asking us for the amount of carbon monoxide. So we would do 0.43 minus 0.11 and we get an answer of 0.320. You could work out the other value. It doesn't ask you to do that in this particular question, but that would be 0.640. We're asked for the amount of carbon monoxide, 0.320 moles. Then it does say calculate the partial pressure of carbon monoxide. Now to do the partial pressure, you need to know the mole fractions. So our mole fractions are our moles of each thing divided by our total number of moles. So we need to add up the total moles in this equilibrium. So we did need that 0.64 in the end. So we add up the three numbers of moles at equilibrium and get 1.07. And we're going to divide each of our moles by the total moles to get the mole fraction. And then to get the partial pressure, we're going to times that by 250 kilopascals. So we want to do 0.32 over 1.07, and we want to times that by 250, and that is going to give us an answer here of 74.8 kilopascals. If we were to work that through in a longer question, we may need all the other numbers as well. If we did do that, we would see we had 150 here. And 25.7 here. And when you add the partial pressures up, they will come to the total pressure. We will have a little bit of a rounding error here, but we will add these up and they would come to our total pressure. Give an expression for the equilibrium constant Kp in this reaction. So what the exam board are wanting here, what we're looking for, is that we have a fraction that we're going to put products on the top line, and then we're going to put our reactants on the bottom line. Do remember that you can't actually highlight in the exam. This is just to help you see where things are going. Now this is Kp, so we need to be using pressures. What we're really looking for is that we don't use square brackets that represent concentration, but we've got the pressure of methanol, a product, and there's only one methanol, so this would be to power 1, over the pressure of carbon dioxide, there's only one of those as well, and then the pressure of hydrogen, there's two of these, so we would be pressure of hydrogen and then pressure of hydrogen again. Remember that the things that are added become multiplied, so 2 hydrogens becomes hydrogen squared. A different mixture of carbon monoxide is left to reach equilibrium at temperature T, and some data is shown. So we've got the partial pressures and the value of Kp, and it wants us to calculate the missing partial pressure. So I'm just going to rewrite, remember we wrote it here, but we're going to rewrite our equation so that Kp equals the pressure of methanol divided by the pressure of carbon monoxide times the pressure of hydrogen squared. And then we're going to substitute in the numbers we've got, or we can rearrange first. So I'm going to actually rearrange first. We want the partial pressure of hydrogen. So I'm going to times both sides by the partial pressure of hydrogen, and at the same time divide both sides by the value of Kp. When I times both sides by the partial pressure of hydrogen squared, the partial pressure of hydrogen squared is going to come up and across to be with Kp, but then I'm going to divide both sides by Kp. So I'm rearranging the equation, and I've got a new expression, this time for the partial pressure of hydrogen squared. So then the partial pressure of hydrogen is the square root of this expression, pressure of methanol over the pressure of carbon monoxide times by the Kp value. So then I can substitute in my numbers from the table. So 5.45 kilopascals on the top there, 125 kilopascals on the bottom, multiplied by the Kp value. And then I can put that into my calculator. And if I do that, my calculator gives me 194.7. And I've got my answer. I could round that to 195 as well, given that all the numbers in the table were to 3 significant figures. Use the Kp value from table 1, so let's just remind ourselves what it was. So it was 1.15 times 10 to the minus 6 kilopascals to the minus 2. To calculate a value for this following expression. So what we need to do is we need to compare the expression we've got now to the expression we had originally up here, and we can see that it's reversed. So when we reverse an expression for Kp, we're flipping our fraction. So our new Kp is going to, if everything that was on the bottom line comes on the top line, it's going to be 1 over our old Kp value, because we're flipping the things from the bottom line onto the top line and the top line onto the bottom line. We type that into our calculator, it's going to come out as 8.70 times 10 to the 5. And if we flip the units, so we do 1 over kilopascals to the minus 2, then we'll get kilopascals squared.